Okay, this multiple choice number 2 starts with number 9 down here. Is a gas in its standard state at 298 Kelvin, which is 25 degrees Celsius. And so on the periodic table, you do need to know that the only gaseous substances at room temperature are over here. There are only 2 liquids at room temperature, mercury and bromine, and everything else is solid. So if you look on here, you can find lithium's over here is solid, nickel over here is solid, bromine, once again, is a liquid, it's one of the few. Okay, uranium, which is way down here, which is a solid, and then fluorine. Fluorine is going to be a gas at 25 degrees Celsius, so 9 is E. Number 10 has 1 valence electron. So valence electrons are the number of the group or family that it's in. Group number 1 has 1 valence electron. Group number 2 has 2 valence or outer shell electrons. Skip across the valley right here because those are a little bit variable. Then it's 3 for 13, 4 for 14, 5, 6, 7, 8. And so has 1 valence electron would be the element lithium right here, which is in group 1. Okay, on the back side, on the next page, we now go to problem number 11. And it says, which species in this is being reduced in the reaction below? And so I'm going to zoom in and assign oxidation numbers for this really quick. Oxygen is -2, which means hydrogen is +1. Oxygen here is -2, which means manganese you have to do a little bit of math for. So figure this out. Remember, ignore the 4. Manganese is some charge. I'll put a blank right there. And then oxygen is -2, and there are 4 of them in this formula. And then that's got to add up to equal -1, because there's a little -1 in the upper right-hand corner, which means manganese is going to have to be +7. So manganese is +7 right here. Over here, oxygen is -2. There's 2 of them, so that means the chlorine here must be +3, because that's got to add up to equal -1 up here. And then over here, oxygen's -2, which means manganese is +4. So my manganese went from 7 to 4, so that went down in charge, so that's reduced. And so letter E is my answer because that's the thing that's reduced. And let's just finish it out here. Oxygen right here would be -2, which means chlorine would have to be +7 in this case to get it to be -1. Hydrogen here is +1, oxygen -2. So chlorine would go from +3 to +7, and that would be oxidized because it's going up in charge. So E is my best choice, or is my only choice. Okay, next problem. In which of the following compounds is the mass ratio of chromium to oxygen closest to 1.6 to 1? So when you see the word ratio, always think fraction. So number 12, what you're going to do is you're just going to look at the fraction of chromium, because it says chromium to oxygen right here. And you're going to take a look on the periodic table and find out what chromium's atomic mass is. And chromium right here is in the middle, it's 52. Divided by oxygens, which oxygen is 16. And if it were just CRO, like it is in letter C right here, you'd do 52 divided by 16 to find that mass ratio. And 52 divided by 16 would give you 3.25, which is not 1.6. So C cannot be an answer. But then if you look back at B right here, notice it's chromium to O2, so then it would be times 2, so it would be 52 divided by 32 for the ratio. So let's do that. 52 divided by 32, I get 1.6, and so there is my ratio that's closest to 1.6. So what you can learn from this sample problem is the word ratio simply means divided by, and then when they're talking about the mass, they just mean look on the periodic table and find its atomic masses, and always read it numerator to denominator when you're looking at the ratio right here. Okay, the next one is actually non-answerable by AP1 students until you get to chapter 20 next year, so you can skip that. The next one is number 15, and this one says, a strip of metallic scandium is placed in a beaker containing concentrated nitric acid. A brown gas rapidly forms, the scandium disappears, and the resulting liquid is brown-yellow, but then becomes colorless when warm. Which observations best support the following statements? And letter D does, because it says scandium reacts with nitric acid to form a brown gas, which is exactly what it told you in the question. So don't think too hard on that one. Just read the observations that they tell you and move on from there. The next one, number 16, is kind of a lab question again. And here we have an empty container, and we have a solid sample of 25 grams and a volume of 11 cubic centimeters. Remember that a cubic centimeter is the same as a milliliter, so don't get confused by that if they switch between the two. And it says the data above were gathered during to determine the density of an unknown solid. Density, remember, is equal to mass divided by volume. So for us to determine the density of it, which they're going to ask us to do for an answer right here, we're going to have to find the mass of this unknown solid and divide it by its volume. So the volume is not a problem right here. It's 11 cubic centimeters or 11 milliliters. So my density is going to equal some mass divided by 11 milliliters or cubic centimeters. Now, the mass of my solid sample and the container is 25 grams. So to find the mass of just the solid sample, I would subtract out that 3 grams. And 25 minus 3 turns out to be 22. So 22 grams divided by 11 milliliters means that I would have 2 grams per cubic centimeter, or 2 grams per milliliter, which is letter C. So just know that you got to subtract out the mass of the container there, and you can do that problem. Number 17. 87 grams of the potassium sulfate is dissolved in enough water to make 250 milliliters of the solution. What are the concentrations of the potassium and the sulfate ions? Okay, so first of all, let's get this to moles. When in doubt, convert to moles. So we have 87 grams of K2SO4. We're told that the molar mass is 174 grams, which helps us up a lot because then we don't have to add up K2SO4 on the periodic table. So let's do that here where we take 87, careful, push the divide by, 174, and I have 0.5. So I have 0.5 moles of the K2SO4 substance. Okay? And now it says it's dissolved in enough water to make 250 milliliters. So if I want to know the molarity of this, it's going to be equal to, or the concentration of it, it's going to be moles divided by my liters. And my liters are 0.25 liters, because remember, 250 milliliters would be 3 to the left, 1, 2, 3, or 0.25. So 0.5 divided by 0.25 ends up being 2. So my molarity is 2 molar in K2SO4. But it doesn't just ask me the concentration of K2SO4, it asks me the concentration of my K plus ions and my SO4 minus 2 ions. So if it's 2 molar in K2SO4, notice that there's a 1 in front of this before it dissociates to form K plus and SO4 minus. So for every one of these, I get 2 of these. So I should be twice as much, or 4 molar in K plus, and I would be a 1-to-1 ratio for SO4, so 2 molar in SO4. So looking at my choices right here, letter E has 4 molar in K plus and 2 molar in SO4, 4 and 2 right here for number 17. Okay, my next problem, number 18, is crossed off, so I go to 19. And this one says, it's suggested that SO2, which contributes to acid rain, could be removed from a stream of waste gas by bubbling it through 0.25 molar KOH, thereby producing K2SO3. What is the maximum mass of SO2 that could be removed by 1 liter of the KOH solution? That's 0.25 molar. And they give me a balanced chemical equation right here. So I'm into my stoichiometry steps right here now. First thing, write the balanced chemical equation. Done. Second, convert to moles. So they tell me that I have 1 liter, molarity equals moles divided by liters. And I want to get to moles. So I'm going to need liters, and I'm going to need molarity. Well, they tell me the molarity right here. So my moles of my KOH are equal to my molarity 0.25 molarity times my liters, 1 liter, which means I have 0.25 moles of KOH. Step number 2 is done. Step number 3, now I do the mole to mole ratio because I want to find out how much SO2 could be used up or diluted or reacted with the KOH. So I have my 0.25 moles of KOH. Put KOH in a position where it's going to cancel, and then put my SO2 as my new set of units. And for every 1 SO2, there's 2 KOHs. That takes care of my step 3. This is moles of SO2, but they don't want to know moles. They want to know what is the maximum mass of SO2. And you'll see every reaction or every answer gives it in grams. And so I'm going to have to ultimately do step 4 right here and convert to the asked for units, which is grams of SO2 in from moles of SO2. And if you look on here, they tell you the molar mass already is 64 grams. But you could go ahead and add up SO2 on the periodic table if you want to. So let's do this on our calculator. We have our 0.25, and then I'm going to divide that by 2. And then I'm going to multiply that by 64. And I'm given that I will produce, or I would be able to neutralize 8 grams of it, which is letter B right here. Okay, my next problem is number 21. And 21 says the correct procedures for a titration include which of the following, and 1 and 3 are correct. Why is number 2 not correct? So rinsing the burette with distilled water just before filling it with the liquid to be titrated is not correct, because if you take your burette and you rinse it with a bunch of distilled water, you're going to end up with little droplets of water inside of there. Even though you rinsed it out, you still have droplets of H2O. And so then when you add your titrant, let's say it's NaOH, for example, you knew that NaOH was a certain concentration. Let's say it was 0.1 molar. Well, now it mixed with those little drops of water in there. It's no longer 0.1 molar. It's a little bit less because it's diluted by those little H2O drops in there. And so part 2 is not acceptable. So C is your answer. Number 22, 1 mole of O2 oxidizes iron hydroxide according to the reaction below. How many moles of FeOH3 can be formed? So we're at a stoichiometry problem again. And the first thing we need is a balanced chemical equation. Okay. And then number 2, convert to moles. And we're told we already have 1 mole of O2. And then step number 3 is the mole to mole ratio. So in number 22 right here, I have 1 mole of O2. And it asks how many moles of FeOH3 can be formed. So I'll do the mole to mole ratio between O2 and FeOH3. And it's a 1-to-1 ratio right here. And I believe that the reason they have the little dots here is I probably needed to go through and check to make sure that I balanced the equation correctly. So I'm just going to check that again really quick. And I'm going to zoom in a little bit closer to make sure that I'm reading the numbers correctly, because I might have skipped step number 1 when I was supposed to go through and do that. So I'm going to rewrite this a little bit larger. FeOH2 plus O2, arrow, H2O, plus H2O. FeOH2 plus O2 plus H2O, and then it makes Fe and then OH3. Okay, now I'm going to zoom back out here, and I'm going to go back and just restart the whole thing, because my mole to mole ratio here I can't know until I balance the chemical equation correctly, and I apologize, I couldn't see the equation quite good enough. Didn't realize that it wasn't balanced right away. So let's go through and let's make an atom inventory. I have 1 iron and 1 iron. Now my oxygens look like they're going to be a problem because I have oxygens everywhere in here. I have 2 oxygens, 2 more right here, and 1 more right here. So 5 total right here. And on this side I only have 3. Yeah, not balanced at all. And then my hydrogens right here, I have a total of 2 plus 2 or 4. And over here I only have 3. So I've got a big problem right here. And to balance this guy is going to be a little bit tricky. Let's try the hydrogens first. 3 and 4. So let's try a 4 here and a 3 here. Nope. If I do a 4 here, then I have to do a 4 here as well. Okay, so that's going to give me 4 irons and 4 irons. And then here I'm going to end up with 12 oxygens and 12 hydrogens. And over here I end up with 8 hydrogens plus 2 more is 10, plus 2 more, 8 plus 2 is 10 oxygens. I'm getting pretty close. Now, I think I could put a 2 right here, and I'd end up with 2 more hydrogens. So I'd end up with 4 plus 8 is 12. And I'd have 2 more oxygens right here. And 2 plus 8 is 10. 2 plus 2 more is 12. Oh yeah, I think I've got it. And so I think that's my balanced chemical equation. And now let's use the balanced chemical equation to answer the question for FeOH3. So there would be a 4 right here, and there would be a 1 right here. So I would end up with 1 times 4, which would be 4. And that's letter C right here. Okay, that took a little while, but thanks for holding on for just a second. I'm going to pause and we'll put the rest of it in the next video.